In the last objective, we talked about receptors in general, and we spoke about the main types of receptors and the ligands that they bind. In this objective, we focus on what happens after the ligands bind to the receptors. So, what happens during signal transductions, with emphasis on the kinases, the ligand gated channels, and G protein linked receptors. So, to start, there are um, signal molecules that bind to receptors that transduce signals. So these signal molecules will bind to a cell surface receptor and activate it by changing the shape of the receptor tail that extends into the cytoplasm. And so in this image, we see a tyrosine kinase that is bound to a ligand. And as we talked about with the protein kinases, these dimerize, and then these actually are phosphorylated. So the intracellular portion of the receptor gets phosphorylated. And what ends up happening is the signal is relayed through a chain of protein kinases to create a signaling pathway that amplifies or eventually alters some cell processes to amplify a signal. So in this image, we see that this kinase will activate another protein kinase by phosphorylation. And this protein kinase will activate another protein kinase by phosphorylation, and so on and so forth. And so this can happen either linearly, where we have an alteration in some cell response, or it can happen in such way that once you phosphorylate one protein, several proteins are able to phosphorylate other proteins within the cell, and this could lead to an amplification of the response or many different responses within the cell. Now, each component in a signaling pathway can either be active, which is the on state, or it can be inactive. To transmit a new signal, every active molecule must be inactivated. Okay? So, in order to transmit a new signal, another signaling molecule can come in and bind and then reactivate everything in the pathway. Now, one of the molecular, or one of the ways that we can turn these pathways on and off is to either add a phosphate group. And so in the last example, we saw that kinases were being added to other protein kinases. And in that pathway, we triggered that cascade of signaling events where we were adding phosphate groups. So when you're adding those phosphate groups, that's typically going to activate a target. Okay. In the last example, we saw that we were activating other kinases in the pathway. Now, remember, I said in order to transmit a new signal, every active molecule must be inactivated. In the cell, there are protein phosphatases that exist. These protein phosphatases will catalyze the removal of a phosphate group. All right? It's going to catalyze the removal of a phosphate group. And in order to break up something, remember, we talked about this earlier in the earlier chapters that in order to break those polymers down, we undergo hydrolysis reactions. Okay? So, in order to catalyze the removal of a phosphate group, they must, under these phosphatases, participate in hydrolysis reactions. So altogether, you have enzymes that are able to turn things on. So your kinases are going to phosphorylate in order to turn things on. And then you have enzymes that turn things off. Your phosphatases are going to participate in hydrolysis reactions to remove phosphate groups from those signaling molecules to turn things off. Next, we have our ion-linked receptors, or our ligand-gated receptors. So many of the ion channel gates remain closed until a ligand binds to the receptor. In the previous objective, we talked about acetylcholine binding to a receptor embedded in the plasma membrane, so binding to one of those ion channel linked receptors. So acetylcholine bound to the receptor, and that allowed for the channel to open, and it caused a flood of positively charged sodium ions. And that influx of positively charged sodium ions led to an electrical signal or an electrical impulse in that cell. Whereas in this example, we are showing GABA, which is another neurotransmitter that can bind to a ligand-gated channel. In this case, this GABA will bind to the ligand-gated channel to open and allow the influx of negatively charged chloride ions. When these negatively charged chloride ions enter the cell, this actually turns the impulse off or inhibits the transmission of a neural impulse. So you won't get an action potential, or you won't get an action from the neuron. Okay, and then finally we talk about the G protein linked receptor and how it initiates signal transduction. So with our G protein linked receptor, or G protein coupled receptor, when it's in its inactive state, there is no ligand bound to the extracellular portion of the G protein linked or G protein coupled receptor. When we take a look at the cytoplasm, another important component, so remember we said the G protein has an intracellular portion that binds the G protein in the active state, okay? So in this particular example, the G protein coupled receptor is inactive, all right? So therefore, the G protein will be inactive. In its inactive state, it is bound, a subunit of the G protein is bound by GDP, okay? When ligand binds to the G protein coupled receptor, now we have the G protein is able to, the G protein coupled receptor is now able to bind the G protein or a portion of the G protein. And one subunit of the G protein will be bound to GTP. All right, so the GDP gets removed and replaced by GTP. Now the active G protein can go on to activate its target. And what we'll learn is that one of the targets for the active G protein is adenyl cyclase. All right, so once the active G protein is bound, it will release its energy by hydrolysis, all right? And then that will convert the GTP to GDP. So now the subunit or the G protein is in its inactive state. So the G protein is now in the inactive state when it's in the GDP bound version. So just a short recap and summary, when we want to compare the actions of the main types of receptors in signal transduction, we've talked about the kinases. So kinases will bind signaling molecules and dimerize and these will also phosphorylate, all right? So when kinases are phosphorylated, that converts them to the active state. Kinases can phosphorylate other kinases, and that will continue to activate things in a pathway. As long as things are being phosphorylated, they are considered active. Now, in order to turn the activity of these pathways off, there are enzymes in the cell that exist. So you have phosphatases that will be responsible for the hydrolysis of those, or dephosphorylating those proteins that have been phosphorylated. Then you have your ion gated channels, or your ligand gated channels. These will bind to neurotransmitters and allow for either positively or negatively charged ions to enter the cell and either activate electrical impulses or inhibit electrical impulses in your neurons. All right, so those were specific examples that we gave as it relates to the neuron. Your G protein linked receptors, these will bind to signaling molecules, and the G protein linked receptor will change its conformation and allow for it to bind to a portion of the G protein. And then the G protein is going to replace the GDP with GTP. So the G protein in its active state can go on to bind its target and then eventually initiate a cascade of signaling events. Now, the GTP bound G protein will undergo hydrolysis, and then the GTP is now replaced with GDP, and that's going to convert the G protein to its inactive